take a look at the structure and some important properties of carboxylic acids. Some of their properties are similar to those of carbonyl compounds, like the nucleophilic substitution reactions that they'll do. They have their own quirks, as we'll see in the upcoming chapters, but still that addition-elimination type mechanism will be common that we'll see coming up later. They have an OH group. They have essentially what's like a hydroxyl group in them, so that means they have strong hydrogen bonding, which gives them high boiling points. A 2-carbon carboxylic acid, like acetic acid, has even a higher boiling point than a 2-carbon alcohol, for instance. So their acidity, however, is their key property. I think probably is the most important property, I guess, to their usefulness. So if I have a base like hydroxide here, we can use bicarbonate. Also, for instance, NaHCO3, there's sodium bicarbonate. We will deprotonate the carboxylic acid by removing the H attached to the O, right? So if you're interested in mechanisms, the lone pair from the oxygen and hydroxide or the other base will attack the hydrogen. Its electrons will go on to the O, giving us a carboxylic acid salt, okay, or a carboxylate ion. So if I had acetic acid, I would now be making sodium acetate over here, for instance. We have an O- counterbalanced by Na+. The equilibrium on this lies pretty far to the right because, remember, what do? We find the strongest acid, right? Water is produced as a product over here. On the other side, we have the carboxylic acid. As we'll see, the carboxylic acid pKs are in the range of 4 or something. Water is around 16, so carboxylic acids are much stronger acids than water. So this reaction will be favored strongly towards the right as it's drawn here, just as a forward arrow. If I have a carboxylic acid that's just on its own in water, it will actually dissociate on its own slightly to a small extent. It's not a strong acid, so it's not mostly dissociated on its own. It dissociates a small amount on its own, forming a carboxylate ion with hydronium. Right, here's our carboxylate with hydronium, and the extent of this dissociation is represented by Ka, the acidity constant. So the concentrations of the two ionic products over the concentration of the molecular carboxylic acid. Right. So in the case of acetic acid, it's on the range of 10 to the -5, something like that. Meaning at equilibrium, we have a large excess of the whole carboxylic acid, and only a small amount has dissociated on its own. But that small amount does produce hydronium ions, which makes carboxylic acid solutions acidic, right? So remember that Ka is a ratio of products over reactants. And when we're talking acid, we're talking ionic or ionized products versus the molecular reactant. So in weak acids, the molecular reactant is favored, so it's always going to be less than 1. But as we approach 1, okay, as we build in more and more of the ionic products, that means that we have a stronger acid. Right? Where it ionizes more on its own, that makes a stronger acid. And since pKa is negative log of Ka, that means smaller pKa values as we approach 0 represent stronger acids. So Ka of 10 to the -5 is a pKa of 5. Ka 10 to the -5 is a pKa of 5. For a stronger acid, we could have Ka of 10 to the -4 and pKa of 4. So let's keep that in mind. As pKa gets smaller and smaller, we're talking about a stronger acid. So as far as organic acids, carboxylic acids are among the strongest. Okay? We've talked about alcohols, pKa around of 16, around that of water. Phenol, right, benzene with an OH was more acidic, okay? pKa around 10, because the minus charge could be distributed over the ring, right? Carboxylic acids stronger than phenols, okay? Here's acetic acid, pKa 4.76. Still not quite as strong, though, as HCl or other mineral acids, right? By mineral acids, we mean sulfuric acid, HCl, HBr, nitric acid, things like that. So for organic compounds, this is about as acidic as it gets. And the reason for that enhanced acidity comes from resonance stabilization. Let's compare acetic acid with ethanol. Okay? Both have two carbons, both have an OH, but acetic acid has this double bond O in it. Okay? When ethanol ionizes on its own, it can make hydronium and an ethoxide ion, but the minus charge is localized onto that oxygen. Okay? It's concentrated, right, very strongly just among that one single atom. So that's an unstable right? That's a fairly unstable conjugate base, meaning ethanol is not a very strong acid. Acetic acid, okay, we remove the hydrogen, we have a carboxylate ion, but there's a resonance structure where we can bring a lone pair on the O minus in to make a double bond, and that kicks electrons up to make an O minus on the other oxygen, which means that in a true carboxylate ion, the negative charge is shared equally over those two oxygen ions. Those are equivalent. Okay? In the actual acetate ion, the two oxygens are equivalent. They're indistinguishable from each other. So because that negative charge is delocalized among those two oxygens, it is more stable than ethoxide, which makes acetic acid a stronger acid than ethanol. Right? Remember, we've done this several times. If you want to think of it in terms of how much energy it takes to deprotonate, something like that. Right, large amount of energy required for ethanol, smaller amount of energy required for acetic acid. Right? Stronger acid because it's easier to deprotonate because the conjugate base is been stabilized a little bit compared to if the minus was just simply localized on that one oxygen.